So our next speaker is Chris Rowen, and Chris has got one of those bios that looks like it's basically 3 careers. So I knew Chris, I first met him when he was VP and GM at Synopsys. We won't mention how long ago that was, but it seems like that was a career in itself. Then he went off and he founded Tensilica.
Fire was invented later.
Let's say the lighter was invented later. So then he went off and he founded Tensilica, was their first CEO for many years, and brought that to a very successful exit, although that also took a few years. We won't go into that one either.
Welcome to the real world.
It was a successful exit, and then he became VP of IP at Cadence. Then he went off and did Cognite Ventures and looked around at a lot of opportunities in deep learning, and something tells me that there's a connection between that and his founding of Babel Labs that I'll talk about today.
Yes.
Yeah.
Thanks a lot, Kurt. Yeah, I think if you sit on the other side of the table and you're investing, it seems from a distance that's going to be really, really attractive to be an investor. But I got to tell you, being an operating guy, running a company is so much more fun because you actually get to have some impact on the world. And Babel Labs is focused on really processing speech, especially speech in extreme conditions, dealing with noise. And we do a lot of work on speech enhancement to subtract out the noise by elaborate deep learning methods. But one of the interesting little sub-problems that's come up is the question of how do we extract noise or really recognize a finite vocabulary when there are a lot of noise and reverberation in the environment, and B, very little power to solve it with. And so this is really a story of putting together a number of pieces toward a solution to finite vocabulary or command recognition in the presence of heavy noise. So first, what does noise sound like? What does noise look like? So on the top, you have a pretty clean command. And with any luck, we can hear that command.
Command 6.
Okay? But that's not the environment in which we're going to control our robot vacuum cleaners or talk to our car or control the music coming from our audio system. Instead, we've got perhaps something as extreme as this, which is exactly the same phrase. You got that, right? But, you know, that's minus 6 dB of noise. So it's about 30 dB. It's many orders of magnitude more noise. And you can see in the spectrogram, you couldn't see it either. You know, there's some faint indications there, but you really want to be able to extract out that kind of noise in the to do these commands. And it's often in mission critical situations. And so we have seen our systems develop that use a lot of computing power to build full continuous speech recognition models, triggered by wake words at the edge. Usually the speech recognition, because it's a big footprint, is running in the cloud. But recognition in the presence of noise represents some serious problems when you start layering on the noise. And we've done some studies of a whole range of different ASR systems, about 6 or 7 of them we've characterized with respect to noise. And they shall remain nameless because I'm using them here to describe the problem, not the solution. So recognition in the presence of noise is something that humans have gotten very good at. You know, not good enough to pick out command 6 from my second example. But even when you can understand it, it's a heavy cognitive load. You know, think about when you were last on a noisy conference call and how you leaned in and you paid a lot of attention and it took your whole brain. I mean, it took your mind away from playing solitaire. That's pretty serious. And so what you find is that if you're trying to do something quite sophisticated, like extracting continuous speech in the presence of noise, it often doesn't go very well. And so here in this chart, we see the noise level. This is really very quiet. When you're getting up here, this is a noisy, fairly noisy room. At the break, we were probably getting into the minus dB range if within a relative to a normal person-to-person conversation. It was pretty loud. And here what you see is the automatic speech recognition word error rate. How often is it getting it wrong? And what you find across a broad set of ASR systems, that when you get up into the neighborhood of 0 dB, you are talking about 30, 40, 50% word error rate. It becomes really gibberish in a lot of circumstances. How do we do better than that? I think there are really two levers. One is building neural network structures that allow us to differentiate speech from noise more effectively. And two is to constrain the problem, that is, to cheat. And cheating is a really important factor in making more robust systems. And what cheating means is that instead of trying to figure out what was said across the possibilities of all possible expressions in the English language, let's aim at just the finite set that we want. And we're only going to listen to those. And we're only going to try to disambiguate noise and that finite set. And so by constraining the classification space, we can make this problem actually a lot more workable. So we've been building a command recognition system with the following goals. We want to make it tiny in footprint. We want something that essentially is free, added to existing silicon. In memory footprint, in power, in compute. We want something which is robust with respect to noise. And a modest goal would mean that we can be maybe 5x better in effective word error rate than a continuous speech recognition system. And we want to span a wide range of vocabularies. And we sort of said, well, let's say up to about 100 phrases, because there's a lot you can say in 100 phrases. And we'd like to be able to adapt quickly to that environment. And we want to be able to handle multiple scenarios. It turns out for different kinds of systems, you sometimes want to be able to say, hey, light switch, turn on. And in other cases, you want to just speak what you want. That trigger serves two distinct purposes. One, you can use it as a form of addressing. That is, of all of the devices that you might have in your environment, which one are you talking to? And second, it allows you to build a smaller, narrower, more specialized network, which runs at lower power, and it is the thing which is always on. And then a slightly bigger network, which is then handling the diversity of phrases that you might use. And we've done examples in both triggerless and triggered systems. If we look at what it looks like now as a signal processing chain, we have a setup that looks something like this. So we're typically doing some normalization of the values. We're detecting activity. Sometimes it's as simple as just looking for audio power as a detector. Under high noise conditions, this is actually a very hard problem because you have to somehow classify, for example, in my hypothetical second example, that minus 6 dB signal, did that or did that not have speech in it? Not an easy thing to tell without actually doing the whole problem. We have developed an optional beamforming capability. And then we go into a fairly classical signal processing pipeline in which we do conversion to the spectral domain, FFTs or MFCCs, do optional frequency compensation for microphone characteristics, and then go into the inference network. One of the keys to doing this well is to be very miserly about resources in that inference network. I mean, the rest of that pipeline isn't terribly expensive computationally, really. And the inference network is going to dominate. And so we've done an almost entirely convolutional network, borrowing a number of ideas from Inception and SqueezeNet in terms of having separable convolution filters and one-by-ones, and a fairly deep stack of these things. So I wouldn't call it a deep network. It has kind of medium depth on the order of 20 real convolutional filters within it. With then lots of scalability in that network to cover a wide range of different kinds of circumstances. Because in fact, if you look across applications, there's wide variations in how much, what error rate people will tolerate, in how much cycle budget they have for their given hardware platform, what their memory constraints are. And so you want to be able to adjust the scale of the model relative to the compute requirements relative to the accuracy requirements. And we've also done implementations across the data resolution space. We have built our own quantizer to quantize down from 32-bit floats, which is what we use for training, into 16-bit and 8-bit ints and other permutations of those. For the way we're doing it, we're taking the whole phrase window at a time and doing a flash conversion of that from waveform to intent. It's not a sequential decode. And that's important to the disambiguation, because any sequential decoding is reducing the space of states of what has already been heard, and therefore limits the ability of the network to change its mind about the closest fit phrase. And this is, I think, one of the things which is appearing to give us significantly greater noise robustness than other approaches to this problem. But one of the byproducts of that is that we really do want to train for that vocabulary. That is, we want a good data set for exactly the set of commands that people are really using. Now, it may be possible to synthesize that. We've been taking a more brute force approach of actually going out to crowdsource and collecting data for the specific command sets. And it's actually worked pretty well in that we have automated a system using Amazon Mechanical Turk and other crowdsourcing methods to be able to collect the data that we want. And we build a web-based query engine to collect up the specific command speech and non-command speech that we want in order to be able to train our systems. And so we're then adding to that significant speech augmentation in the form of not just adding noise and reverberation, but doing a variety of other transformations to the utterances themselves in order to magnify the apparent number of speakers and the apparent number of utterances that we're using, so that the total amount of speech that we're using in a training run is in the 50 to 100,000 seconds of speech in a single training run. And since these are quite small models, that's actually quite a bit of data. I'm sorry, 50 to 100,000 unique utterances, but then they're augmented, and then we have epics, so that we're talking about 100 million utterances as being a typical training run. But fortunately, that's something that we can do in a few hours of training time. So in fact, the data collection and the training is converging towards about a 2-week turnaround time from command set to being able to do it. So what does the behavior of this system look like as a function of model size? And we use, and I'm representing the results here in 2 different ways. So each of these curves is a different model. And there are 4 model sizes I describe here as nano, extra small, small, and large. So nano is about 20 kbytes of model. It's a tiny model and requires about 4 million multiplies per second. So it's a very low compute footprint. And lo and behold, it's not the best. It holds up actually fairly well across the spectrum, but when you start getting up to about 5 dB of noise, you start to see some meaningful degradation. As you move up to the extra small is actually, it looks like a pretty good compromise in terms of holding up. And it's still only 45 kilobytes of coefficient and about 16 million multiplies per second. All pretty modest. We also measure it by computing the effective word error rate for this reference command set. And I'll talk about the command set that's used for this in a moment. But these are typically phrases of 3 to 5 words, so that we can get a rough comparison of what the behavior of these commands are versus the expectation for continuous speech. At 0 dB, you remember that other speech recognition system was probably up in this neighborhood of 50 to 60% word error rate, whereas the better models here are around 10%. So it's looking pretty good for disambiguation leverage relative to what people do if they rely on the continuous speech recognition methods. So let's talk a bit about command sets. This is the reference command set that we use for this experiment. So this is 35 distinct intents. We came up with a broad set of commands that you might use to control your thermostat, your lights, your television, and commonly used functions on your smartphone. And we came up with a range of different possible expressions of how to say things. So you might say, what's the time? Or you might say, what time is it? You might say, answer the phone, or answer telephone, or answer mobile. You've got that diversity, which effectively gives you the opportunity to have a more natural language interface. That is a key element in being able to make this as natural as possible. In this particular case, we don't have any trigger phrase. Everything is a trigger phrase. And that involves some trade-offs. On the one hand, it means that you only have to run a single network. You have a very intuitive usage model. On the other hand, you have 35 times as many possible false triggers. And so you have to, you sort of have a larger attack surface, if you will, for noise on the behavior of this system. We've also built systems that have a classical trigger phrase followed by one of these commands. And generally speaking, well, it's a little bit more complexity because you run a trigger model and then you run the command model. But it does mean that you have that first level model, which can be smaller and or more robust relative to false positives. So let's think a little bit about implementation. The good news when you have models that are requiring only, a few, maybe tens of millions of multiplies per second, we don't have to play very many hardware games to get to something kind of interesting. Now, you certainly can, and there are exciting opportunities to drive the power here down into the tens of microwatts by applying hardware optimization methods. But what we've done is said, well, there are an awful lot of existing silicon out there that's going to be able to deliver cost effectively the tens of millions of multiplies per second that are required here. And so when we go to implementation, it's actually a pretty interesting flow, because the original network is developed and trained in TensorFlow. And then we built a custom quantizer, and that generates C data structures. And then we do a scalable, kind of a configurable C implementation that works across that whole configuration space of the network structures that we support. And that uses DNN libraries or DSP libraries where available. We've done 3 ports so far of this. We've ported to the NXP IMX RT 1060, which is a Cortex M7 CPU. We've ported to the Ambic Apollo 3, and we've ported to the Tensilica Hi-Fi Fusion F1 DSP. And we have sort of a snapshot of about where the the megahertz requirements are. This is for the small model. This is something that nominally requires about, what did I say? 16 million multiplies per second. And so it's fairly efficient. And I'm sure that there is, a little bit more megahertz to be had in getting there. But these are rough approximations of a pretty good implementation for it. It's also pretty small. The nice thing about a neural network is that it's such a regular structure that it's a tiny library that you need to implement it. And so the code is only about 5 kilobytes of code, including the FFT and the normalization and all of the classification. The model size itself, mentioned, was about 45 kilobytes. Memory buffers are sort of the same order of magnitude. And so the total footprint, some of which is in RAM, some of which is in flash, is only about 100 kilobytes for this. Now, this wasn't the most accurate model, but it gives you an idea of the range and some sense you can sort of do the arithmetic on the others. So that we're expecting that 100 kilobytes, 200 kilobytes will be typical sizes for the recognition function. Now, of course, an application is going to do a lot of other things around this, but it's a reasonable starting point. And then we can also look at some of the power characteristics. I happen to have chosen the Tensilica Hi-Fi as one example. But this is a consideration of the power associated with the core and its memory, not whole chip power. There are some excellent platforms out there. I mean, the low power characteristics of the Ambic platform are impressive. The general purpose microcontroller, the NXP M7 is a little bit higher end, but also very good from a power standpoint. And we're also starting to work with Sentient on looking how we can map this onto that ultra low power analog neural network structure as well. But you're talking about something which, when you take together the core compute power, the approximate local memory power, leakage under typical conditions, you're only talking about 400 microwatts to do a significant speech recognition problem. And we think that's really something that has the potential to be quite ubiquitous, particularly where this problem of neural networks in the presence of noise is critically important. And so the automotive environment, speech IoT, not just in the home, but let's say in the kitchen, on the factory floor, out in the outdoor environments where there is wind and traffic noise and other environmental considerations, make it really important. I think this is a step, at least in that direction, and it has some key implications. I think command recognition plays an important role in speech-powered systems, particularly when you consider that there are environments that are inherently noisy. There are environments where privacy is critical, and you don't want necessarily to involve the cloud in the processing of that private speech. You want something which is more robust, especially if you're in an area where the network isn't always available. And clearly there are places where you want to operate at lower energy on batteries or in very cooling constrained places. I think command recognition complements heavyweight continuous speech recognition in many applications. It essentially is a way to skim the cream off the top and reduce the load on the heavy-duty computing. It's another layer in that cognitive hierarchy that comes up again and again when we start talking about tinyML. But it is an example here of fairly careful co-design of the signal processing stack, the neural networks, the code implementation, and the training system together to build something that allows people to move rather quickly to deployment of these kinds of systems. And there's a lot of likely refinements. I mean, it's not just possible, but I think it's very likely that people will come up with even tinier networks. They're going to leverage more specialized hardware in order to get energy minimized DNN reference. And there's lots of opportunities to push the envelope on vocabulary richness and really explore that boundary between the constraining of the vocabulary that allows us to essentially consider all possibilities in parallel, and the desire to have much richer vocabularies that you would ever want to try and train as a flash recognition system. So thank you very much, and hopefully there's time for a couple of questions.
So you're at a different type of deep learning conference when the large model is 100 kilobytes. That's got to be a landmark. So question here. Yeah.
Hello. So did you also consider LSTM networks as a candidate, and why did you choose CNNs?
Well, I mean, I think part of the key to disambiguation is to have all of the information about the utterance be available at once. And so there's no need for any history. You don't have to remember anything about the past. You have the whole 1 second or 2 seconds associated with that utterance in front of you. And it's not even all that much data, because if you look at it in the time frequency domain, you may have 100 time steps times, 50 frequency steps. So it's not very big, and you quickly reduce it. And so I think it's, in a sense, an LSTM is just a way of summarizing the past and inherently throws away some information about the past, hoping that your network has learned to remember just the important bits. Yes.
So I'm curious, the noise that you tested your network with,
yeah.
What kind of noise was it? And if you were in a situation where, like here, for example, when we have a break, many people are talking,
yeah,
presumably that should be a lot harder kind of noise to deal with than just, completely irregular noise.
Yeah. So we have, pulled together a corpus of about 15,000 hours of noise from a huge variety of sources. So it's noise from bars and cafes and conferences and fans and wind and sirens and babies and all kinds of things. And we've used a sampling of that noise. It's a very diverse noise set. And so we use different samples of that for the training and for the testing of it. But it's a quite rich mix. Primarily non-stationary noise, so varying noise, which is naturally harder than stationary noise. But I can talk to you offline about the specifics. I also, I think, can run a little demo of it for you on my laptop for those who are interested. But not now.
There's a couple more questions.
Yeah.
All right. I agree that the neural networks have a lot of structure to them that should allow for very tight code, as you mentioned with the 5K.
Yeah.
We've seen a number of excellent examples today of implementations that mostly look to be proprietary in having developed that.
Yeah.
We've also seen recently TensorFlow putting out their TF Lite implementation. I'm interested in your thoughts about frameworks for tiny machine learning networks. Most people seem to build their own. There's this movement for sort of open source platforms. I'm interested in your thoughts as to how we're finally going to sort of get to a rich platform for building these things quickly.
Yeah. Well, thanks, Kevin. I think it's useful to separate it into, very crudely, tools and IP. And clearly, everybody benefits from better tools. And the state of it ain't that good today. I mean, it's actually pretty decent for these low-end machines.
We're going to the tools session here. So.
Yeah, but when you get up to building things that run on these obscure, fancy parallel networks, I mean, it's not do they work or not. It's just in how many ways are they broken that you have to do. I mean, a drawer here I work with, his job seems to consist of discovering the 47 unpublished footnotes that constrain it. So we have a really bad tools problem today. I think it's good news if people are innovating with respect to network structures and not just saying, well, I used ResNet because it's the one thing that the tools allowed me to run. And so I think that we're going to see this explosion of new structures that people use for neural networks as they make trade-offs. And the interesting thing about it that we certainly discovered is that there are better networks and worse networks, but really almost anything will work. If you have enough parameters, you can make anything work.
And enough data.
Well, yeah, certainly if you have enough data, but you can make it work. And so there's not, you don't debug the networks, you sort of explore the space of how optimal they are.
So let's take,
Yeah.
there seems to be lots of interest. Let's take
So yeah,
one last
the question is this command speech command set can detect from the continuous speech string, or just you have to, take, for example, 1 second's speech as a command, then detect it.
Yeah, the latter. We're really, we can, in general, we're picking out that key phrase anywhere it appears. So we're listening to continuous speech. So you can say, please do command 6, and it will find that. And we're taking the brute force approach of training for those specific commands because that gives us the greatest noise disambiguation.
Okay,
Thank you.
well, Chris will be here, so
Yeah.
during the poster session, and maybe I know you're disappointed, but didn't you used to work for Chris or something? So, I think he's got some shills out there. Thank you, Chris.
Thank you.